The next session is titled Getting Started with Machine Learning, Core Ideas and Models. And it is taken by Professor Anil Kumar S. And we are proud that he has been with our institution till last month. And now he has got a transfer to our sister institution, Government Engineering College, Idukki. And uh, he has been a great academician and has got immense experience behind him. And he is currently a research scholar in IIT Madras. Uh, and with your permission, let me welcome Professor Anil Kumar S for the session. Thank you.
Hello. Can you hear
Hello,
me?
yeah, audible.
Yes,
Thank
sir.
you.
Yes.
Thank you, Professor Shibhuma, for inviting me into this session. Okay, and I'm Anil Kumar from GEC Idukki. This session is actually a practical session where we'll be familiarizing basic machine learning models. Let me cut my video first so that I'll take the presentation. So in this session, what we are trying to do is we'll experiment with certain supervised machine learning models. So in the last session, Professor Kumar had already explained what actually is a supervised machine learning. So let me go to the basics of supervised machine learning first. See, supervised machine learning, as you know, is learning something under the guidance of a person or under a supervisor. So to build a machine learning model, who can serve as a supervisor? Here, the supervisor means we are giving some data where the input and the required output are known to us. And we are actually creating the model for giving the output for a particular input. And we are actually trying to teach this model with certain data that when this input is given, you should give this output. In that way, we are giving several inputs and we are getting several the corresponding outputs. That is the way in which we are trying to teach the model. Therefore, this data where the input and the output we already know, we call it as a labeled data, and that serves as the supervisor for such learning. And in unsupervised learning, you know, you will never give such kind of data. Say that model will actually do its learning process by analyzing the patterns in that, and that type of models will be used for tasks like clustering, association, etc. Now, in our session, we will be familiarizing only supervised machine learning model. So, what is actually our aim by designing a supervised machine learning model? Let me look at what is the aim. So, you will be given some inputs. For example, you will be given the features of, you will be given the details of, say, sugar, pressure, cholesterol level, etc., creatine, all those levels of some persons, and our aim is to give a model which can predict whether that particular person is having high probability of getting cardiac arrest. Think about such a model. It can predict whether a particular person is having the high probability of getting cardiac arrest based on some features. Let it be some sugar value, pressure value, cholesterol value, but maybe some medical parameters. Yes. Here, what we are trying to do is we will be mapping our inputs like sugar, pressure, cholesterol, these medical parameters to some number which can give the probability of getting the cardiac arrest. So our task is actually here to find a function that maps the inputs to the correct outputs. That is actually the goal in designing this model. And this type of modeling, supervised machine learning modeling, is actually used for mainly two types of tasks. That's classification and prediction or regression. Regression is actually a kind of prediction where we'll be predict only continuous values, not categorical data. We will predict some continuous values. Classification means you will be given some inputs, like I already explained, whether that particular person is more is having the high probability of getting cardiac arrest, yes or no. Say yes or no. Say if you have chest X-ray images of chest X-rays of persons, then we want to classify whether a particular person is having say pneumonia or not. Here, each data is categorized into two, that is either having pneumonia or not having pneumonia. So that's called the classification. The input is actually categorized into several categories, which we already know the number of categories already. So the two tasks that are commonly done in supervised machine learning are classification and prediction or regression. Now, in this session, so we have actually two sessions. In this session, what we are trying to think about regression models. So let me first discuss some basic supervised machine learning models. They are the linear regression model, decision tree model, and support vector machine. Linear regression means so you will be mapping your input features, input parameters to the output by means of a linear relationship that we'll see later. What is actually a linear relation between the parameters and the output. And this is called a parametric model. It's called a parametric model where in modeling you are actually trying to find certain parameters based on your labeled data, what we call as the training data. In the second type, that is a decision tree. It's something that we normally use in our daily life. Here, normally this is done for classification. It can also be used for regression. But we'll be having a set of features given to you, and we'll be analyzing, or we'll take the features one by one, and using the values of these features, we'll be doing some classification. Some features will be more useful in giving the correct class than the others. So based on that, we will be having several trees that we can see in the next session. We'll actually discuss decision tree in detail. And this actually, decision trees are used for classification mainly and can be used regression also. But in our session, we'll use only for classification. And finally, the support vector machine model, that's also a classification model where you will be finding an optimal boundary among two classes. It's actually used for a by-categorization mainly. See, we want to fit a particular optimum boundary between the two classes with a parameter called a margin. We'll be choosing the best margin. We'll be choosing the boundary in such a way that we'll get the best margin possible. So that we will also see in the next session. Now, in this session, our objective is to study the basics of linear regression and explore what is actually polynomial regression. And we'll see how these are actually implemented using some Python code. And finally, I'll give a brief discussion of the issues called underfitting and overfitting with a brief discussion of bias and variance. And we'll also give some basics of how the regression models, that is the predicting models, are actually evaluated. What are the performance measures for prediction models? These are the main objectives of this particular session. And in the next session, what we are going to see is we will be implementing our classification models. We'll be mainly seeing three models, that is the logistic regression model, then the decision tree model, and the support vector machine. These are the three models that we will see in the next session. So let me come to what is actually linear regression. So a linear regression is actually predicting a numeric value output from some input features. People will call these features are independent variables and the output as dependent variables. And we assume that there is a linear relation between the input and the output. For example, it is normally known that the weight of a particular person and the height of a person are actually related by means of a linear relation. That's the exact relation is actually given to be height in centimeters. Height in centimeters is equal to weight in kilogram plus 100. Height in centimeters, you take that as y for your output as equal to weight in kilogram. You take that as x, your input plus 100. So here actually what you have done is you will be relating your input weight and the output height by means of a linear relation. And here we have only one parameter, that is height, one independent variable or one feature, namely weight. But in general, we can have a number of features in addition to, say, what I told, like sugar value, pressure value, cholesterol value, any type of any number of parameters you can have actually. And one another thing is, we assume that these parameters are actually independent, meaning is that they don't have a relation between them. Like some parameters say x1 and x2 are there. You don't have case like x2 is equal to 2x1, x2 equal to 3x1. So we assume that there are no such relations and these parameters are assumed to be independent. And you are actually trying to form a linear relation connecting these parameters x1, x2, x3, etc., xn to the output y. And you can see that in equation, y is equal to alpha 0 plus alpha 1 x1 plus alpha 2 x2 plus etc. alpha n xn. Here, x1, x2, x3, etc. xn, we are assuming them as actually features and this y as our output for this dependent variable. And what is actually modeling such a linear regression model? Meaning is you will be given some data. So we get data values for x1, x2, x3, etc., xn, and you will be given the corresponding y value also. Your task is to find what are these parameters alpha 0, alpha 1, alpha 2, etc., alpha n, that will best fit this particular data that is given to you. And you are actually giving the input as well as the output, that is your training data, and based on that, your task is to design alpha 0, find out the values of alpha 0 to alpha n. That's actually called designing a linear regression model for the particular data that is given to you. And when you design such a model, you should have some measurement. You should have some basement by which you will be choosing the values of alpha 0, alpha 1, alpha 2, etc., alpha. What is the basement? The basement is we want to minimize these predicted values of y and the actual values. That is, when you are giving some x1, x2, x3, etc. value for a model, it will be predicting some value. Maybe call it as y cap. The actual values are given to be y. Actual value is given to, so there is an error y, the actual value and the predicted value, y minus y. And this is true for every such data. For example, you will be designing a model, you will be designing the measuring the lengths, measuring the heights and the weights of 100 persons from a particular village, and we will be designing a model based on that. Suppose that you have got the weight, height in centimeters is equal to weight in kilogram plus 97. And after designing the model, you will be given some other particular weight values, and you will be measuring the height values. And maybe the resulting predicted values may not be exactly same as the height values of those corresponding data. So in that case, there is a difference between the predicted and the actual values, and we want to minimize this difference so that the model is as accurate as possible. And that's our aim. And how that is actually working. So you will be given, I told there is a training data that is given to you. In the training data, there are M samples. Maybe you can think about it as the M, that is data of M different persons. What are the data? Maybe X1 may be the sugar value, X2 may be the pressure value, X3 may be the cholesterol value, and X4 may be the creatinine value, maybe like that. X1 sugar, X2 pressure, X3 cholesterol, and X4 may be the creatinine. And you will be given 100 samples, where each sample corresponds to each sample has these 4 values. And each of these samples corresponds to one particular person's data. And we also know whether that particular person is having cardiac arrest issue. So that is also known to us. So that is why I gave each sample xi1, xi2, etc., xin with the corresponding output yi. So for the first data, first person sugar value, first person's pressure, first person cholesterol, first person creatinine value, and the y1 value is whether that particular first person is having the cardiac arrest. What is the probability? Maybe 0.8 is more probable. There is a high probability that he is getting cardiac arrest. Maybe the second person's, that is pressure, sugar value, cholesterol value, then the corresponding y2 value will be given the probability. So you will be given such a table of data where you will be having one set of columns corresponding to your features, and the last column corresponds to your output. And please note that there is only one output that is predicted here. That means your dependent variable or output is only one. There you can have several independent variables features. And our task is, using this data, you will find out the values alpha 0, alpha 1 to alpha n that will best fit this particular data. So that after finding out this alpha 1, alpha 0, alpha 2, etc., alpha n, if you substitute these values again, you will be getting the most accurate results. And for that, what we'll be, see, as Professor Govt told, we'll be using certain loss functions here for computing this alpha 0 to alpha. Here, we will be using a loss function called sum squared error, SSE, and some people will call it as the mean squared error, where this SSE divided by the number of samples m. Both can be used, both will give the same result. Sum squared error. Look at that. What is actually that? That's actually y1 minus y1 cap. You will be using y1 cap means it is the model that is predicted. That is the value that is predicted by the model, or that is predicted by the model for the first sample. Y1 means the actual value of output. So y1 minus y1 cap means how much deviation is there from the actual value for the first predicted value. And it is done for the second deviation between the actual second value and the actual predicted value for the second sample, for the third sample, fourth sample, and you will be taking the square of this. Why you are taking the square? There are actually two reasons. There maybe I am not able to explain the exact reason, because there is something called a continuity issue. People may say why you are not taking the errors, actually y1 minus y1 cap plus y2 minus y2 cap plus y3 minus y3 cap. That is actually the total error. But there is an issue is that here y1 minus y1 cap may be positive, like plus 2. y2 minus y2 cap may be minus 2. So when you add, these two will be getting 0. Some positive terms will cancel off other terms. So that finally there may be a possibility that the SSC may be equal to 0. That doesn't mean that the model is the best model and it will give always the correct answer. That is not the mean. So this type of issues may be avoided if you are able to make the sign of all these deviations same. So we will be able to make the sign to be positive by several ways. One way is to take the absolute value of the error, that is modulus value of y1 minus y1 plus y2 minus y2 cap, like that. But we are not normally taking it actually, because in the actual derivation of this, we will be using some differentiations here. And the function y equal to mod x is not differentiable. It is not continuous at the point x equal to 0. So normally that type of mean absolute or absolute error is called AE. That is not taken. Rather, we will be using the squared error. Since you are squaring each error, you will be getting positive, and y equal to x square is always differentiable, and it is continuous throughout the range minus infinity to +infinity. And based on this, we will be computing the values of alpha 0, alpha 1, alpha 2, etc., alpha n. And there are two ways for to computing this. One way is there is a normal equation for computing this. Given this data, there are equations for computing this alpha 0, alpha 1, alpha 2, etc., alpha n. That is actually a matrix based equation. And the thing is that it's actually a very time complexity. So it's actually very computable. It's actually a computably expensive operation, means it requires a large number of computations for computing this data, computing these coefficients, especially when the number of features n is large and when the number of samples m is also very large. So therefore, what we will do is practically we will go for an optimization technique called gradient descent method. Gradient descent method, where that is actually used for finding the optimum point, or to minimize a particular function. The technique that is used in mathematical optimization to find the to minimize a convex function, minimize a convex function. I'm not explaining. If we have time, then we'll explain what actually gradient descent. And please note that these techniques are actually we are using in our daily life, even if we are not cared about this. We are doing this gradient descent method. Now, let me come to this later, key features of this. Let us see about what are the types of linear regression. There are mainly two types of linear regression. They are the simple linear regression, where you will be having only single feature, which I already explained. You will be having only height as the dependent variable and weight as the independent variable. Height is equal to weight plus 100. Weight plus 100. Here height corresponds to your, why I am writing y cap. Y cap I am writing because the value that is actually predicted by the model is may not be exactly equal to the true value or the target value. That's why I gave a cap notation to make sure that to make it clear that there may be some difference between the predicted value and the true value. And we have only one, see, in the simple linear regression, we have only one independent variable like our weight and one dependent variable. So our relation is actually y cap is equal to alpha 0 plus alpha 1x. And the case that I already explained is about actually multiple linear regression, where you'll be having a target value y cap and we have multiple features x1 to xn. And your model is actually alpha 0 plus alpha 1 x1 plus alpha 2 etc. alpha n xn. And now what I'm going to do is I'm going to explain how such a model is going to be implemented using Python. And for the implementation, I used a data set called position salary data set. I obtained this data set from Kaggle platform, and that data set is actually nothing but giving some designations and the corresponding salaries for those particular designations. And these designations will be indicating by some level numbers. That is what is, And that level is, that means for this particular level, this is the corresponding salary. For the, see, level number 1, that salary is maybe 20,000. Level number 2, salary is 30,000, like that. Here level is our feature or independent variable, and the target is actually or the salary, which is the salary for that particular level. And we will be using the Python code, where we will be having the package scikit layer and pandas and NumPy, matplotlib. Matplotlib is actually not for the implementation; it's only for showing some plotting some these points. And the most important package that we need are pandas, NumPy, and the scikit layer. And now what I'm going to do is I'll be explaining how that is implemented. So let me change this slide for a while. Hello, sir. Have you given that code to the participant?
Yes, the the link for the code is already placed in the chat window. Also, it has been emailed and has been provided in the WhatsApp group. So I will once again paste the link for the code in the chat window. Yeah, I have once again placed it in the chat window. So it is in this particular drive that the programs that the resource person has given is there.
Okay. Okay, thank you, sir. Now I'll be implementing this linear regression, simple linear regression in Google Colab environment. And this program is actually given to you, that is given actually available in the link that is provided to you. If you want, you can copy it from there, and you can to copy it from there to this Google Colab in your machine, and you can run it. And I'll actually illustrate how this is actually implemented. I think this is visible to everyone. This Colab environment is visible. So here I have used the position salary data set that you can see in the right side tab, where some positions are given. That's actually some strings, and there is 3 columns: position, level, and salary. Position is actually a string which corresponds to what is the corresponding level. Here we take only level. That means business analyst means it's level number 1, and junior consultant level number 2, like that. So we'll having several levels and the corresponding salary, and we are going to design a linear regression model that will connect the salary and this level by means of a linear relation. Okay. So what I have done is I uploaded, actually imported the pandas packages and the linear model. Actually, a train test split. Actually, I am not using it here because I wanted to use it for explaining overfitting and underfitting also. And this matplotlib is actually used for plotting these points. What are the actual points and what are the points that you obtain by means of the model? And so what I'll be doing first is I'll be say there is a salary data set assigned. PD means it's used for creating data frame. Data frame, maybe you maybe think it as like a table like this. So you will be creating a table using the position salary data set. Maybe you can think it's called a data frame actually. And you will be having the frame named salary data set. In that, we will be extracting the column. The column named level will be extracted to a vector called X, and the column named salary will be extracted to a vector named y. So you will be having x vector, which is representing the values 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Just like you are an input array in C program, you can treat like that. And y may be treated as an array like 45,000, 50,000, like that. They will be having only the corresponding salary value. Now, the next operation is actually not used here. Actually, when we design a model, supervised model, what we normally do is we will be using only a part of the training or that given data set for training, and the rest is used for testing whether the model is actually performing good or not. So you can have several kinds of partitions for the data. You can have a 70%, 30%, 70% for training, and 30% for testing, 80% training, and as you like, you can do. Here I just shown such a function actually, but I didn't actually use here. That is for partitioning this given data x, y with a test size of 0.3, meaning is that 30% of the training, the whole data is used for testing, and the 70% is for training. And accordingly, I actually extracted the training data, that is x train. It is the inputs for the training. Y train is the corresponding outputs for the training. X test is the inputs for, that is the level values for the test data, and Y test is the corresponding salary values for the test data. And then we will be designing, create the linear regression model, and we will be designing a linear regression model by using this linear regression model dot linear regression, a function named the linear regression. Using that, from this package, linear model, by calling this linear regression function, we'll be creating the linear regression model. And see that in this case, what I used is I used fully the whole data X for the training. That's why I told I don't have actually, there is no use in this particular example for the train test split, because I just want to show something which is related to underfitting. So I'll be use the full data for the whole 10 values for training this for the model, and then I'll be using the same model to predict those values. So the same inputs I have. So that means I have given some data to the model for getting the alpha 0 to alpha 1 values. Then I use the same data, input data, and then check whether, then find out what are the values predicted. Then let me run it. This is when we run. So this is the data that this is the result that I am getting. See this here, the red line is actually showing the alpha 0 plus alpha 1, right? Alpha 0 plus alpha 1 x value. So here only x value is the level value and y value is the salary value. That is the relation. So you will be getting a straight line here. But you see the actual points I have plotted in blue. See that? And there is one outlier also that is actually far away from the line and far away from the other points also. The last top right point is an outlier point. And see that only for the third and the fourth point, the model is giving somewhat correct value. And for the others, the actual value that is given by the model is, or predicted by the model, is too far away from the required value. So what is the conclusion is, this model is not able to predict, is not able to capture this data very well, so that this model cannot be used as a useful model for predicting the salary given the level number. And we can actually see, without plotting, we can see that by using some parameters called R square number and RMS. R square is a value that we'll explain later. So so that is the inference that we got. So what is the solution? So we should, so this model is not having the, is not able to capture this type of data. So you see that that data is not actually actually lying on a line. So this means this data is not a linear data, or this model is actually very simple and is not able to capture the complexity of the data. So therefore, what we will do is we'll go for alternate type of. That means models which are able to do this. That means models with more power, and that is discussed next, and that's called a polynomial regression. And one more thing that I want to say, when you have only one feature, that means independent variable x is on the right left x-axis, and your dependent variable y on the y-axis. So you will be having a straight line as your relation. When you have two independent variables, x1 on the x-axis, x2 on the y-axis, and your predicted value y on the z-axis, at that time, so the linear extension in 2 dimensions, that is actually plane. So when you will be getting a plane in that dimension, so you will be having alpha 0 plus alpha 1 x1 plus alpha 2 x2. And when you have three features, x1 x-axis, x2 along y-axis, x3 along z-axis, and the y along the fourth axis, where you will be calling such curve as a hyperplane in the fourth dimension. So what actually you are trying geometrically, you are creating a best hyperplane that will fit your data. That's actually the aim when you speak in terminologies of geometry. Okay. Let me come back to your slide. Here, last time what we have done is alpha 0 plus alpha 1 x. We didn't take any square terms. We didn't take any cubic terms, fourth power terms, etc. So that's why it is called linear. But in this, instead of fitting a linear relation between the input and the output, we are trying to fit a polynomial relation between the input and output. Like a function of the form y cap equal to alpha 0 plus alpha 1 x plus alpha 2 x square plus etc. to alpha n x power n, where our target is, or our aim is to fit an nth degree polynomial connecting this feature x with y cap. Then you may be asking, what will be the situation when there are two features x1 and x2? Then the situation is y cap is equal to alpha 0 plus alpha 1 x1 plus alpha 2 x2 plus alpha 3 x1 x2 plus alpha 4 x1 square plus alpha 5 x2 square, like that. In all possible combinations you should take. Like if you have, that can be treated as a polynomial in two variables x1 and x2. So since it's complex to explain, I just consider only a polynomial or a case with only one independent variable x. So what I have done is I have taken more terms, more coefficients. So that is actually a complex model than the previous. So alpha 2. So this is actually fitting. I am fitting a nth degree polynomial connecting x and the input feature and the output. So in our case, our level case, suppose you are fitting a 10th degree polynomial, meaning is that salary is equal to alpha 0 plus alpha 1 into level plus alpha 2 into level square plus alpha 3 into level cube plus etc. up to alpha 10 into level power 10. Up to 10th degree term you are taking. So that more information can be captured by using the coefficients alpha 2 to alpha 10. So normally, this regression can also be considered to be a linear regression, where you can take x as your x1, x as your x1 first parameter, x square as the second one, like x2, x cube as the third feature, x3, like that. if you take the x is equal to x1, x square is equal to x2, x cube is equal to x3, like that x power n is equal to xn, the equation becomes alpha 0 plus alpha 1 x plus alpha 2 x2 plus alpha 3 x3, etc. up to alpha n xn. So these x1, x2, x3, etc., xn, which are actually they are actually the powers of the original feature. They are sometimes called the polynomial features. They are called polynomial features. So we'll be using that polynomial features in the implementation of such a model. What I'm going to do now is to design a polynomial regression model for the previous data, and let us see what is happening. So let me change this slide. So the second tab, in the second tab, I'll be implementing the polynomial regression. And the features as actually the ideas are all same. We'll be using the SK scikit-learn package, NumPy, Pandas, Matplotlib, etc. And I told this x square, x cube, x raised to 4, all those are considered to be the polynomial features. That means just by using linear regression model, you can also find out polynomial regression model. But the thing is that you should take x1 as x, x2 as x square, x3 as x cube, like that. So that is what is actually, I just have done the same steps here. I extracted the position salary data set into a data frame, and I extracted the input level into one vector x and the output into y. I then splitted that is into two parts, training data and testing data, with 30% for training, testing, and 70% for training. Here also I didn't use this. And you can see a statement like PR assigns polynomial features of degree is equal to, what I'm going to do is I'm going to set degree is equal to 2 now. What I'm going to do is I'm going to find a relation like salary is equal to alpha 0 plus alpha 1 into level plus alpha 2 into level square, second degree polynomial. Instead of, previously you have only alpha 0 plus alpha 1 into level, that's all. That actually created that so much error that you already seen. And what happens when degree is set to 2? And then I designed using the same linear regression model. I actually I created a polynomial regression model, the linear regression, same function. But the thing is that x1 as x, x2 as x square, like that. So we can treat a polynomial regression as a linear regression with n variables, with the n independent variables, which are actually the powers of the original independent variable in the polynomial regression model. Now I'll be fitting that original polynomial features with y. Now I'll be plotting these points and I'll be taking the errors. Now see. Now you see this model is able to capture something better than the previous. And you can see that R square value is actually better. Previously it was R square. I told R square closer to 1 means it's actually a better model. Previously it was 0.66. Now it's actually 0.91. And you see that the points are actually very almost nearer to this, but some points are actually far away from the predictions. So this is for degree 2. Now, what I'm going to do for degree 3. And see, please note, previously the your RMSE, that is a mean squared error. RMSE means, anyway, you take this SSE value, that is for each point, you take the difference between the actual value and the model predicted value, then its square, sum up all those divided by the total number of samples, then take the square root of this. Why you are taking the square root? Because you have already taken a square. So you want to take a square root. Our root mean square error. And see that that is 1,63,388 in the first case when you are having a simple linear regression model. But when you designed a quadratic regression model, what you got is actually your RMSE is reduced to 82,212. So almost half. So you may think it will be okay when you set more degree, that is degree 3. Let me degree 3. So that's more better. So you can see it's something better than the quadratic. And see R square is now nearly 0.98 and RMS is nearly 30,931. So almost again less than half of the previous. So I set 3 instead of 3, I set some 5 degrees so that I have alpha 0, the salary is equal to alpha 0 plus alpha 1 level plus alpha 2 level square plus alpha 3 level cube plus alpha 4 level power 4 plus alpha 5 level power 5. That is the relation that we want to keep. Let me see what is the so if it's something better than the all the previous one. See, your RMS value is surprisingly reduced to a 4-digit value, 4,047. That's very too much, nearly 1/10 of the previous. So you may be think, oh, very good to design such a model. See that your model complexity is being increased. You are designing more complex and more. So let me set it as some 10, so that you will be having up to alpha 10 level power 10. So very nice. You see your R square value is almost 1. Maybe, and RMS value, see this is very less. Meaning is that this model, the 10th degree polynomial model, is predicting this training data, the output for this data will. So this is better model for this. Oh, okay. Okay. So what will, let's see what is happening. What was actually happened in the previous case. When you were actually taking your model to be linear regression model, so you see that the error was too high. What is the inference? You actually designed one model using some data, and you told that for this particular level, that is the salary. You for level 1, this is 45,000 is the salary. Level 2, 50,000 is the salary. You told actually. After creating the model, you again gave level 1 as the input, but it gave a different value, not 45,000. Meaning is that you gave the training data itself to the model, but it gives the values which are far away from the actual values required. So that means the training error is very high. Or we say that the model is underfitting. We'll explain that. The meaning is that that model was very simple enough, very simple, and is not capable of capturing the complexity in the data. Just like I'm trying to teach the differentiation for a 4th standard student. We know a 4th standard student, however brilliant he is not having, normally is not able to find the derivatives of the function. So what should be the other thing? That student is not having the capability. So we should improve the complexity of the model. That means we are making 7th standard, 10th standard. That was actually done by increasing the degree. Now you may think, so if you increase this degree, so it's good. Anyway, you got to 10th, better. So now you are having very good. Let me set degree as 50. So that this is more complex than. Now also this is good. You cannot see too much difference. So it is 15th degree. Now I'm going to make it as 18th degree 80. See this, surprising. See, when you were having the degree only up to 10, your RMSE was 0.000 something. But in this case, RMSE is increased. So after increasing the complexity of the model beyond a point, the predictions are going to be wrong. Predictions are going to be. So increasing the model complexities infinitely is not good. It's not good. That's the point that I want. Now, how we can avoid the, let us come back to our underfitting situation. Underfitting. So I'll be closing this window and come back to it. Underfitting means a situation where the model is too simple to capture the patterns in the data and leads to poor performance for both the training. That means the data which you actually, that means we are all teachers, we are doing some problems, say for example, calculus problems in the class. And after doing some problems in the class, we are actually giving the same problems to the student, but the student is not able to solve the same, that problems themselves. So they're actually making mistakes for those problems which we already covered. That situation is called underfitting. How we can avoid this? The thing is that one reason I already explained, that student may be a student in the 4th standard, in the 5th standard. If you are actually teaching matrix multiplication or actually trigonometry for the first, those students, even if you solve any number of problems, I think it's not useful. So you should increase your model complexity. Like you should teach a 12th standard student, or at least 11th standard student, those ones. So you increase. Now that means increase the model complexity. That's so that you have seen when I increase the degree from 1 to up to 10, that underfitting was actually resolved. Now the second method actually is we'll use more features. Sometimes the features, for example, to capture the cardiac issue, maybe the sugar, pressure, cholesterol, and what creatine value, they may not be sufficient. Maybe you may be requiring some other values also for predicting that. Therefore, in some cases, this may occur due to the lack of the proper features in your data. That may happen. That may happen. And there are several types of such data in your Kaggle in that. For example, you can see a data like for bank chain prediction. In Kaggle itself, there is a data set. If you use that data set, you are always getting very, very wrong results because the features that are given in that data set are not appropriate for predicting the bank chain. And another thing is, we'll be training, we'll be giving more and more samples. That See, after doing some 2-3 problems, if the student is making the mistake, then what we'll do? We'll do more problems. We'll solve more problems in the class so that the student is more learning more about that, so that this student will be able to solve the problems later correctly. So that is the situation of underfitting. Now let us come back to the case of overfitting. So this is underfitting. I just illustrated with a figure. So the model is actually a straight line. See, the green points are the actual points. See how far these points lie from this line. You can see. So the model is not at all good. The next situation is a very interesting situation, which we already normally see in our daily classes. More overfitting. This is a situation where a model, after designing a supervised model, it will perform very well when the training data itself is given. So you have created a model. After creating the model, you gave the same training data. You get the excellent results. Excellent results. Just like you are trying to solve a number of problems in the class, and when you give the same problems to the students are all performing very well. They are giving the correct answer. But at the point when you are giving a different problem, they are not able to give the answer. So you just say, instead of say what is d by dx of sine square x, so instead of say, maybe they will be writing that is 2 sine x into cos x. But at the point to write it is cos square x, they may be making the mistake. That means even a small change in the training data, if you make a small change in training data, and if we give that change data, the model is not able to correctly give predict answer, or the model prediction is very wrong. That means the error in the training data for the training data is very less, but when you give a different data, test data, it will give a very bad results to us. Such a situation is called overfitting situation, and it's actually a treatment of how well the model is behaving when a different data set is given. So normally when we teach, what we do is we will be giving some problems to the student. We all teachers, all of us actually want our student to perform very well when they will be given different problems. Even if we had not solved those problems, our aim is that the student must be able to solve problems which are actually different from those we actually solve in the class. That's our aim. So if that is actually achieved, meaning is that our student is not having the overfitting issue. Instead, we are doing some programs or problems in the class. Student is able to write it, and that is actually seen in many of the courses. Say like in programming courses, when we will be giving some number checking like primality checking or perfect number checking or abundant number checking. So whatever, see that when we are solving the problems in the class, and after solving, and when we are asking them to write the program, they will be writing very well. But at the moment we change a program, the question, the student will be in trouble. There we say that the student is in the overfitting situation, the sitting situation. Such a situation arises due to several reasons. One thing is, let me take a simplest a case where assume the situation where the cardiac arrest data set is being prepared by a particular hospital, by Chennai Apollo. So they will be actually recording the student sugar, pressure, cholesterol, creatinine values of the patients that are actually visiting their hospital versus their whether they have the cardiac issue. They may be doing this for some 2-3 years, and after doing this for 2-3 years, they will be getting a very big data set. Okay, what are the features they are recording? They will be recording sugar value, pressure value, cholesterol value. Maybe suppose that they may be recording the height values of the persons. Height, what are the height or the height values? See, one thing I'm sure, I'm not sure whether height is having any relevance in cardiac arrest. I think there is no relevance. On that assumption, I am explaining this example. Simply they are recording this height values also. So in their actual data set, some unnecessary feature is, see, some height feature is also, sugar value is there, pressure is there, cholesterol is there, creatinine is there, height value of the person is there, some other values are also there. And we are using these 5 instead of the 4, we are using the height values also for prediction. In fact, so that there is a term alpha 0 plus into sugar plus alpha 1 into pressure plus some alpha I into this height will come into picture when we design the model. And this alpha I will be contributing something to the model, and see this height is not having any relevance in alignment with this cardiac arrest. So this unnecessary feature is playing some role there. So we can treat that as a kind of noise data. This unnecessary feature is playing the role there, and that will make some issues there. And due to that, this overfitting may occur. So what it will do is that it will just by heart what we are actually trying. What we are actually giving as input, they will be trying. See, they'll be studying. And at the moment, a different input is given with a different value for the height. It may think that the height is having true relevance because of the alpha I feature, and it will give a. In fact, there is no relation for this. There is no connection for this height to the cardiac probability. So this noise data is making the issue there. So unnecessary features may do the problem. And another cause is the high values of the model coefficients. So if I'm going to explain that, I need to explain regularization. I don't get the time for that. So these are 2 desirable situations, 2 undesirable situations in supervised machine learning modeling. And now see this data. So this data, to capture every data, this model seems to be very complex. That is why it is very zigzag patterns are seen. Zigzag patterns are seen, so that we are designing a very complex model. Say previously, say in the last model that I created with the degree equal to 18, that was actually an overfitting model. If we change a little bit of the program, we can see it's actually an overfitting model. Now, how this situation can be actually understood, how this underfitting and overfitting are actually, how they are characterized. See, to characterize this, we'll be using 2 terms called bias and variance. Bias is actually measuring how well our model, our predicted model, captures the exact relation in the training data. So there is an exact relation in the training data. If our model is able to correctly capture the exact relation, for example, height is equal to weight plus 100. If the model is able to predict a relation like height is equal to weight plus 99, we can say that our model is almost capturing the true relation, that is the linear relation. But instead, if you relay, like I just gave an example, height is equal to 0.1 into weight square minus 0.3 into weight plus 227. This model is not capturing the exact relation is a true linear relation, but the relation that I told is a second degree relation is not capturing. Therefore, that model will be giving, even if you give the training data itself, will be giving a very wrong answer. So this bias will be actually measuring the quality of your model with respect to the training data. Meaning is that how well your model capture the true relationship in the training data. And to find out this, that is what you have to do is what actually task to measure this bias actually. What you will do is that, suppose that you will be having a model, you will be having a training data set with you. Suppose it has 100 samples. Let it, you assume like this, 100 samples. What you will do is that you take some samples of 60, for example, 60, say 10, 3, 4, 5, some 5, 60 samples. You take some 60 samples first set, 60 samples second set, 60 sample third set, 60 samples fourth, 60. So you take 5 subsets of your original 100 sample data set, and each subset has only 60 samples, assume. And using these 60 samples, you design a model, maybe a polynomial regression model of degree 3. Degree 3. So using the first subset, you are designing one model. Using the second subset, you are again designing a degree 3 model. Third one degree 3 model, fourth one degree 3 model, fifth one degree 3. After creating all this, you will be taking you have the 5 models with you. All the models are created out of 60 samples from the original 100 samples that is given to you. Now, what you have to do is you take the first sample from your given data, give to the first model, second model, third model, fourth model, fifth model. Each one will produce one value. Say, first one will produce the value, say, y1 1 cap, next one y1 2 cap, y1 3 cap, y1 4 cap, y1 5 cap. Y the first one is for the first data. Y11 means the output for the first model for the first data. Y12 means the output for the second output for the first data by the second model, like that. After, for the same data, these 5 models will be giving different predicting values. You take their average. It's not the average, it's exactly the expectation. You take the average, so you will be getting a single value. Now you subtract this single value from the actual value of that particular sample. You have y value, subtract this y value from this average value. Now do this the same for all the data. Do the same for all the data. So you will be having a collection of deviation values. Take their average. Take the average of these deviations. That will be giving you the bias values. That is the way in which bias is actually measured. And when the bias is undesirable, when high bias means model is very bad and it will have both too much error in the training and the testing. And low bias means our model is good model and is able to capture the exact relation in, like you have seen in the 10th degree polynomial. You can see that our model is capturing almost 100% of the true relation in our data. Now the variance is actually a measure of how well our model performs when it is given a different data set. That means actually it is created using one data set. So when that data set is given, okay, it will perform very well. Just like our student is by hearting. Whatever we teach, he will be writing exactly in the answer sheet. But at the moment when a different data set, when a different question is given, so if he has studied very well, then he will also answer that questions also correctly. But the situation where he is not able to answer those questions which we have not solved. So such a situation is that the training error is very less, but when a different data or questions are given, the error is very high. The meaning is that even if a little bit change in the questions are made, samples are made, say the model will be too much sensitive so that the variation between predictions, say if we change is very, very large. That means suppose you have given the weight value as say 50. Suppose it is given in the training data 50, so it will predict some 150. But at the moment you make it as 50.2, it may give some 179. At the moment you make it as 49.7, it will give some 168. Like that, that is. And then you make changes. So the variations in the predictions are actually more. So that is what is called a variance. It's a measuring the deviation, of the different predictions from the average prediction values. It's actually measured by using the normal variance parameter in statistics. We take the variance of the prediction values, and if our model is overfitting, our variance will be too large. And there is an equation that connects this bias and variance. And so there is a derivation piece called bias variance trade-off. And this equation says that this total error in system is equal to bias square plus variance plus irreducible error. Irreducible error means those errors which we cannot actually measure and reduce. It may be inherent in that system. Maybe due to there may be some floating point issues in the computing devices. Maybe it may be having some precision up to this. You are not able to, however well you are giving the data, you are not able to predict. You are not able to improve the precision of your floating point representation. Such type of irreducible errors are always there. Leave all those things. So all the reducible errors that's equal to bias square plus variance. Meaning is that when you try to improve the, when you try to decrease the bias, there is variance is getting increased. Variance is getting increased. And when you try to decrease the variance, then bias is getting increased. And there is a normal explanation. Why does this happen? And it's actually an analytical type of explanation. What will happen when variance is improved? What happens to the bias? What will happen when the bias is increased? Why the variance will be decreasing? And if I get time after this, I will explain what is the actual reason why variance is decreasing when bias is increasing, and variance is increasing when bias is decreasing. And see this. This is about the complexity of bias. See that I'm plotting the model complexity along the x-axis and the error on the y-axis, and you see that the total error is actually shown there. And you see that for lower values of the x-axis, the bias is actually higher values, but their variance is less. But as you improve the model complexity, what you can see, bias is becoming less. As what you have seen in the last case is when the degree was 1, you have some error, degree was 2, the bias training error was reduced. Degree 3, degree 4, degree 10, all those things are good. But when you increase the model complexity, there may be a chance of increasing the variance. So that is actually what happened in the 18-degree polymer. That model was actually forfeiting there. So I have to make some changes in the program so that I can, if I get time in the next session, I will be explaining why it is. We'll be giving a program for that also. And see that there is an optimum point where there's a trade-off. You cannot increase the bias too much. You cannot increase the variance too much. And so there is an optimum point, and that point is actually shown there. And this is the desirable point for a machine learning model. And the same situation is actually shown for this bull's eye diagram. This bull's eye diagram, this center red circle is showing the desired point. And this is actually, this diagram connects what variance with the bias. There are 4 possibilities: low variance, low bias; low variance, high bias; high variance, low bias; and high variance, high bias. See the leftmost situation, low bias and low variance. That is the most ideal situation which we want. That means training error is less and the model is good when it is given with a different data set. And that is what is shown. Almost all the points are near in the bullseye. The bullseye are the actual points where we want. They are the actual target output values. So see that all the blue values are actually within this bullseye. But when you see low bias and high variance, that is the first row, second column, what you see. See, due to high variance, see the points, the predictions are actually scattering around the bullseye. The variation, see the prediction for one sample is totally different from the other one, So that even for small changes in the input, it is giving very, very, very different values for the high variance and for the low bias. that situation is called the overfitting, because that's top row, right column. That situation is actually the overfitting situation. Here the second row, first column, where you will be having high bias and low variance. See, high bias means your actual predictions are far away from the bullseye, which are the exact points, the red circle. But they are having low variance. That means the low variance means their predictions are almost in a vicinity of region, in a small neighborhood, so that there is no considerable difference between the various predictions. So it's maybe just like having accumulating these points in some vicinity of this particular vicinity of this area. And finally, that is the situation where you will be having high bias, and that situation refers to the situation of underfitting, where we will be having high bias. And finally, the most worst situation where you have the high bias and high variance. See, so the points are actually far away from the bullseye. That means high training error, and there are considerable fluctuations in the predictions, even for small changes in the input. So the points are scattered, and that is the most undesirable situation. And finally, I'll be giving a small illustration of how you will measure the performance of regression model. Actually, there are several measures. I'll be explaining only two. Actually, some absolute error is also there. I'll be using only two measures. Actually, sum squared error, SSE, and R square. This R square is the most important parameter for regression model analysis. It's called the coefficient of determination. It's actually logically that performance parameter is designed. We'll be seeing how you will be doing this. Sum squared error. This is the thing. Sum squared error. What you will be doing is that for each data, you will take the actual value, you will take the predicted value, take the difference, take their square, and do the same for all samples. Add up all these, and this will be giving SC, sum squared. That is the sum of the squares of the error. That is, error means the actual value minus predicted value. And if you take, or if you divide this SSE by the number of samples n, what you are getting is the mean square error. Mean square error. And if you take the square root of this, you will get root mean square. So if you have this, this SSE is less, that means our model is good. If you are getting models with lesser sum square error, means that your model is a good model. What about the coefficient of determination? It's actually too significant. See, the equation y is computed. 1 minus sigma I ranges from 1 to n, yi minus yi cap whole square by sigma I ranges from 1 to n, yi minus y bar the whole square. I'll explain what it is. The top one is SSE itself. 1 minus SSE divided by one parameter. What is that? That parameter denominator is actually taking the deviation of actual value, taking the deviation of the actual value from the each actual value from the mean actual value, or it is the variance of the exact output values. So you are taking 1 minus SSE divided by variance of the exact value. And you consider a situation, this R score is equal to 1. Why does it, when does it happen? When R score is equal to 1 means the second term is 0. That means that sigma that cap A by B term is 0, meaning is that the numerator is 0. The numerator is 0, meaning is that every squares are, that is, sum of the squares is equal to 0. Sum of the squares equal to 0 means each term is equal to, that is yi equal to yi cap. That means for each point your target value or the exact output value is you are getting as the value predicted by the model. That means the model is able to correctly predict the output for each point. That means R square is equal to 1. Now considering a situation where R square is equal to 0, that means your second term is 1. When the second term is 1, means that A by B equal to means that A is equal to B. That means yi cap is almost equal to y bar. Yi cap is almost equal to y bar in most of the samples. That's why you are getting R square is equal to almost 0 value. Yi cap, because in both the cases, the first term is yi minus, in the denominator is also yi minus. Yi cap, yi bar. That means y bar means it is the mean value, mean actual value. So in that case, what does the model actually do? The model, you give, say, you give some one sample, maybe it is giving, say, predicting the value as 100.2. You give the second sample, it is also giving the 100.2. Third sample, again giving 100.2. What is this 100.2? This 100.2 is the sum of the, is actually the mean of the actual predicted value, actual output value. So that model will be just behaving like an average predictor. That's all. It's a very bad model. So our aim is to obtain models with values, with high values for the R square. And that is what is aim. So R score is equal to 1 means perfect fit, and equal to 0 means no better than mean. No better than mean means our model is just a, whatever data we are giving, it is giving some mean value as the output. That's all. And that's all about our discussion. And I'll show one more code for illustrating the overfitting, underfitting. This is a linear regression. You see, this is a linear regression model. This is for the training data. It's very, very simple model. See, this is a very randomly chosen data set. Data set is actually chosen. I have chosen some random values like this. You can see some random data I have generated. And for those, I have created a linear regression model. And the model is too simple. It's the underfitting situation. For the testing data is also test too much. See the line there and see the points actually line.
Sir, are you sharing the screen? It's not visible now.
No. I'll be able to. Okay. Sorry. So is it visible now?
Yes.
So this is a code where I have illustrated overfitting and underfitting. I just created some random samples, just random samples. Not random samples, I just initialized some samples. These samples, I actually tried several samples, and a lot of effort. I could get some samples so that I can illustrate this point, model complexity. See this, how polynomial regression with the degree 16 I created. See the model, how exactly the model is actually behaving to fit. So it's too much complex model, creating the overfitting situation. And this is for the testing data. Degree 16, and we can try, and I gave you the code, and you can try it with actually, I just created two models. One is a linear regression model using this, and the second is a quadratic, is a polynomial regression. And you can see by just changing the degree in that, there is a variable called degree. You can see that the model is getting improved for up to some degree increase, and later after increasing beyond a level, the model is actually getting worse and worse. That is what is called as a overfitting situation. And that's all about our presentation. And if you have any doubts regarding, please.
Thank you, sir, for the presentation. Is there any question from the side of the participant?
Hello, sir. Am I audible?
Yes, sir.
And sir, you told about that bias between, we have to juggle between the bias value and the degree of polynomial to avoid that overfitting. Now, whenever we are starting a model, where to start actually? Where to,
So that
and
is
what are
thing.
exactly,
Actually,
what
there is
should be our start point? Is it like whether we are taking 100 as a bias value, 90 as a bias value, or 80 as a bias value? We
no,
go
no,
on.
no. Actually, there are some methods for that. The thing is that you take some. There is something called a true function. Notion of true function. So there
Okay.
should there's true function means the actual relation in that. So when see, I actually started with a simple model for the data, and you see when I gave the same data itself, I got a too much training error. So at that moment, you should understand that that model is actually underfitting. That model is underfitting, meaning is that is not able to capture. Therefore, you should think about some other model which can improve the performance. So
That's it. So that means we have to do some hit and trial initially.
there is otherwise we should be having some true knowledge about the exact relation in this data, and this is one of the challenges in measuring the bias. When we read the materials, you can see that the true function. See, when somebody is giving a data set to you, it may be consisting of too much values. You may not be aware of what is the true relation in that. If you are all okay that the true relation is actually is a third degree polynomial, okay, you can start with the third degree polynomial. I'm starting with third degree polynomial. In that case, it will give the correct. If you are not able, then what you have to do is you should start with a simple model, and with then you should measure this performance, and gradually if the increase the performance or increase the model complexity till you get a good model. That's the only way, unless you know the true relation for the true function, which is the actual name is true function in the input data.
Okay. Thank you, sir.
Okay, I think that concludes today's session. In this second session by Professor Anil Kumar S, he started with uh, the topics of supervised learning and then moved to linear regression and polynomial regression, and he has shown practical examples of uh, these regression methods, and then he moved to bias and variance and how underfitting and overfitting can happen, and what are some possible remedial measures for avoiding these things. And on behalf of Department of Computer Science and Engineering, Rajiv Gandhi Institute of Technology, uh, I would like to extend our sincere thanks to Professor Anil Kumar S, and we are lucky that he is continuing the first session tomorrow. And thank you once again.
Okay. Thank you, sir.
And thank you all the participants. You have been here for the past 3.5 hours for getting new knowledge and new insight. And we hope that your enthusiasm will continue in the coming days also, so that this STP will become really fruitful. Thank you.
Thank you, Anil Kumar sir. Thank you, sir.
Thank you, sir.